Alright, welcome to stoichiometry. This is section 9.1 and 9.2, introducing mole ratios, and then actually finally putting together chapter 7.3 and chapter 8 together to really do what we consider actual chemistry. Now this little stoichiometry mole island diagram helps to help you see what we're doing here, but I don't expect you to memorize this. The idea is that you're doing the same conversions we've been doing the whole time, and that less memorization and more practice will get you there. So some key vocabulary in chemistry. The mole ratio is another conversion factor where you have moles of substance A over moles of substance B. This will have a relationship of one substance to another. Coefficient should seem familiar. That's again the number in front of a compound or element. Ideal just means that everything works out, all the reactants are used. In the next section we'll look at a non-ideal reaction. Conversion factor, that's the same idea of this being an example, a ratio. And then moles are the idea that these are these 6.022 times 10 to the 23rd particles again. But we often won't use particles because we're looking at dealing with masses. So let's looking at our intro questions. Be sure to answer those before you move along, and those will be gone over when we come back to class. So the problem types that we have four different types. When we have the given and unknown are moles, so that's a moles to moles conversion of one substance to another. A moles to grams, to where we have moles of one substance to grams of another. From a grams to moles, or a grams to grams, which is number 4 is going to be our most common because we measure in grams. We often want to know in grams how much we produced, because in our everyday life we work in grams. Now we're able to relate one substance to another by looking at the chemical equation, like one given here. It's balanced and it shows the relative amounts of each reactant and product, not only from one side to the other, but to each other. So there's many mole ratios for this example, and I try to look at how many we start off from the left all the way to the right. Now generally listing them off may be a question or two on your test or on your homework, but it's just being able to recognize all the different types. So if I started off, I can show a 2 moles of HGO is going to relate to 2 moles of Hg. And that is equivalent in value of its reciprocal. I think I'm using the right math term. 2 moles of Hg over 2 moles HGO. So those are equal in value, and those are 2 of our many types of mole ratios. Again, depending upon your situation, you'll use one or the other. Another example, again, is our 2 moles of HGO all over 1 mole of our O2. You see the numbers come from the coefficient in the equation. And again, that is equal also to its reciprocal. You are required to write down the chemical formula of what you're talking about. This is more important now than it ever has been, because as we transition from one substance to another, that will be required so you can see what you're transferring to. And then we have our 2 reactants we can even have a mole ratio for. It's not just reactants to products and vice versa, but also includes our reactants. Because what this is saying is that for every 1 mole of oxygen that is made, I will also make 2 moles of mercury. And that can be important because maybe the mercury is easy to determine how much I made, but the oxygen is not. It's a gas that would leave the air, as this is a decomposition reaction. So I might be able to measure the mercury and determine by math how much oxygen was produced, and that can be extremely handy. Again, mole ratios will just be another conversion factor that we'll use now in the middle of going from one substance to another. So in this section, we're looking at what are called ideal calculations. A systematic approach is very similar to one that we've been doing the whole year. That's why I've been teaching it that way, because it's useful the entire year long. They're ideal because all of the reactants are used up perfectly. Now, ideal isn't a real situation, but it's a simple way to start, and then we can deal with the more challenging real-life situation. So I'm going to use this formula that you see down below. This is a chemical equation, and use this to relate to go from grams to moles, moles to moles, moles to grams, and grams to grams. Essentially giving you an example of one of each of the four types. Alright, so let's take a look. I've already kind of written this on the next slide so we can see. If I was to produce, or wanted to produce, 12 grams of nitrogen monoxide, I would like to know how many moles of ammonia I need to start with. So, like always, when we're doing our conversions, what goes on top goes on the bottom, grams of NO. Now, grams is only related to moles, hence where we have our molar mass. Again, setting up our conversions with our units first is most important. Again, what's on top on this first conversion factor should go on the bottom, moles of NO. And our new conversion factor, the mole ratio, will relate moles of one substance to moles of another substance, in this case, moles of NH3. So now that I have all of my characteristics here, my units set up, I look and fill in my numbers for these. Now, moles of NO, I look at my chemical equation, and I see it's every 4 moles of this for every 4 moles of NH3. Don't take the time to reduce it, just leave it as is. Especially if it's like 6/2, you might think it's 2/1 instead of 3/1. There's no point to put your brain through more stress than it needs to be. As for our molar mass, it's always so many grams per mole, which means 1. And we need to calculate the molar mass of nitrogen monoxide, which is our 30.01 grams. So we're multiplying all the numbers across the top, then dividing by numbers on the bottom to see how many moles we're actually going to produce. Now remember, significant figures are about the numbers you started with. It does not deal with anything in the conversion factors. So all 3 of these are significant, so I should have 3 significant figures. Your calculator should tell you 0.3998. Because that is an 8, I need to round up and get 0.400 moles of NH3 as my answer for this. And again, zeros to lead the number are not significant. Zeros to the right of the decimal at the end of the number are significant. So we're going to look at the next example here. Let's go with 17.4 moles of water. And how many moles of ammonia? Again, it really doesn't matter which one, you just choose different mole ratios to help you relate. So again, what's on top you copy down to the bottom, which would be moles of water. And what's on top is moles of ammonia. So, looking at our chemical reaction, I see that there's a ratio of 6 of these to every 4 of these, based off the coefficients in the chemical equation. Again, multiply the numbers across the top of the conversions and divide by the number on the bottom, and my answer gives me a nice 11.6 as my answer of moles of ammonia. Again, the format is much more the same. Alright, so let's look at a moles to grams amount. Let's go with 0.300 moles of oxygen, 2 grams of water, let's say. So, again, set up what's on the bottom, moles of oxygen. And at this point, when I'm in moles of oxygen, and I started in moles, I need to get it to the other substance, which is water, in which this is where I'm going to use my new mole ratio in order to translate one substance's value to another substance's value. Now from here, I have moles of water, because that's what's on top, gets transferred down to the bottom, and I can always relate moles to grams of water. Remember, for every 1 mole, I have my molar mass, which I'd have to calculate, 18.02 grams per every 1 mole. And I look at my mole ratio for my coefficients here, 5 moles for everything here, 6 moles here. So now that I have that set up, multiply everything across the top, divide by the numbers on the bottom individually, and I get 6.4872 grams. I see 3 significant figures, so that becomes 6.49 grams of water are produced. Let's see, produced? Yes, produced when so many moles of oxygen are used as a reactant. Now for the last one, which is our most practical, and it would be our longest, but I don't think the difficulty is any different. Let's say I had 10.0 grams of oxygen, and I need to see how many grams of nitrogen monoxide are produced when all of those 10 grams are used. So, again, what's on top will go on the bottom. And in this section, if you ever have grams, that's always going to relate to moles as our molar mass. When we have moles of O2, once we've translated it to moles, we want to translate that to our other compound. This is our opportunity. It's our doorway to go from one substance to another. So I'm going to utilize that. So, as we have what's on top, that will go on the bottom. So moles of NO will relate to grams of NO. And again, I've previously calculated these for every 1 mole. I look at my balanced chemical equation to relate my mole ratio. So my balanced chemical equation tell me the numbers that go filled in there. And when I think of my 1 mole of oxygen, that's 32.00 grams per mole. So multiplying everything across the top, dividing by the numbers individually, so you do everything across the top, divide by 32, push equals, divide by 5, push equals, will give you the answer of 7.50 grams of nitrogen monoxide. So on this slide here, I show the steps in full detail of how to go from the most challenging of grams to grams. However, the fact that we have grams to grams, it could be grams to moles. You have to identify that again by putting what's known on the left and what your unknown is on the right to help guide you to how far you need to go. Please answer the questions and do the end of the 3-2-1 so we can come in to see what kind of questions you may have. You will get lots of practice in class and more guidance as we go throughout. However, a lot of this should seem very familiar as it is a continuation of conversions which we will continue throughout the rest of the semester. I'll see you soon. Bye-bye.